welcome from my side as well. So who is PROTOS? PROTOS builds software tools, domain-specific language, modeling tools, test tools, software architecture, and the like for embedded systems. And I am Thomas Schütz. I'm an aerospace engineer and have a lot of experience with embedded software architecture, but also how to build tools, tool chains, and especially test tools and code generators and so on. So what is it all about? The first question always is why? Why are we doing what we are doing? Late testing is a real problem in the software development in general, but especially in embedded development, because the later test phases like a system test or integration test, or also after the release, they get really, really expensive. And usually they're not done very often because they are so expensive. So if you're lucky, you can get a test every couple of weeks or months even. So what we do with the mini-hill, we bring a huge part of the system test and the integration test to the developer, to the desktop of the developer, while he's developing it, and reducing the turnaround cycles for testing to minutes instead of weeks or months. So that's the basic motivation for the mini-hill. Let's have a look at the usual development cycle of a test of an embedded system. Usually you start on an evaluation board. Many projects, that's the way to start. On the right target processor, you configure your drivers, and you program hardware-related software components, for example, a motor control, a battery control, low-level bus systems, protocols, CAN bus, LIN, and so on. And on top of that, you put your software components and you integrate everything into your application. In the end, you move to the real hardware, to the real electronic control unit. And yeah, so the question is, where do you test your application? Usually, those are the spots where you actually test something. In most projects. So for example, the pure software components, you can test very good with unit tests. That's cheap, that's fast, that's good to automate, so please do that. But not all the software components are ideal to test with unit tests, especially hardware-related software components, such as a motor control system or something like that. That's really hard to test with a unit test strategy. So usually it's not really tested in the early stages of the development. Later, usually you have a system test, a real system test, or a simulated system test, for example, a hardware-in-the-loop system test. But that's usually very late in the process, very expensive, and not very often, because the equipment and the tests are so expensive. You do not get a response time, very fast response time. So, and that's exactly why we invented the mini-hill. The mini-hill is focusing on the early stages of the development, or basically on the complete development cycle, with a focus on helping the developer testing his software development during while he does it. So, but on the right processor with the complete software stack usually. So that's basically a hardware-software integration test. So your complete software as it is on the right microcontroller. So it's basically the smallest possible hardware-in-the-loop test system. In most embedded projects in those phases for a very long time, they are not tested in a structured way. So what do I really want and need? What I really want is, I want to test what is changed most frequently, and that's your software. It's not the hardware. The hardware at the beginning maybe changes every couple of weeks, later every couple of months maybe, but your software changes several times a day, or even more if you have a bigger team. And so you want to test for every code change of every developer within minutes instead of weeks or even months. Then you want the full regression test also for unrelated code, because you know the situation, you change something over there and suddenly something over there doesn't work anymore. You have side effects in embedded software more than in a normal software. You have restricted resources. You have, for example, shared resources like IOs and interrupts and so on, or also the memory. So you want a full regression test, or you need to run a full regression test after every change. The next thing you want is a full test automation to enforce tests. So you want to find out about every change, whether it works again, and you can use continuous integration to really do that. So every commit needs to be tested within minutes. And the last thing is you want an automated hardware in the loop test to test more than pure software units, because it's not a pure software system. It's a system in a combination of hardware and software. So you need at least to test at the signal level all the IOs you have in your system, and by that testing the complete software. So the question is now, why is it so hard to automate tests for embedded systems? I give you an example from a motor control system for an oil pump. It's safety critical. For example, in this case, they need to test the temperature shutdown for all border values for 300 relevant system states. That's a lot. So a couple of thousand tests maybe for temperature shutdown. What they had before, they had a climate chamber with a complete ECU, with the power electronics, with all the sensors, and even the real motor, the pump, and the hydraulic system. So climate chamber is really big, 2 meters by 2 meters or something like that, and it's very slow. So theoretically, they would have needed around 30 days to test all those border values or boundary values. And so it never happened, because usually after a couple of hours, the system fails. So the climate chamber reduces the temperature, and suddenly the hydraulic system gets stuck because of the low temperature. That's normal. So, but then you open the chamber, you repair the hydraulic system, you put in more liquid or whatever, and you're back at 20 degrees plus. So you need another 2 or 3 hours to wait until the temperature is down to minus 30 degrees maybe. So that's really, really hard to automate such a test. So it basically never ran automated completely. So what we did is we took out the microcontroller with the complete software, including all the drivers, and created a black box test with a mini hill at the pins of the microcontroller. And now we have a simulated environment. So whatever happens, we have it under control, and we can stimulate, we can do a failure injection, and on top of that we put the test cases, and suddenly we are down to 50 minutes for complete test suite for the complete product, completely automated, and it always runs through. So that's really simple to automate, because you take the hardware out of the loop, so the real hardware, the motor and so on, because that's not what you want to test. You do not want to test whether the motor works. You test this once and that's it. So now let's have a look at the different test levels and different test methods you need to test those levels. So we have again the same system, with the hydraulic, the motor, the ECU, and so on. So usually you can start with a unit test for single software units, like a C module or a class. That's a unit test. You can use a unit test tool for that. The software integration test for pure software integration, that's something where you also can use a unit test. So you have more than one unit and integrate them. That's a software integration test. Still, you can use a unit test system. That's easy to automate. That's fast. So please do that. So the next level is a bit harder to do. That's the smallest possible hardware in the loop test. So the idea is you look at the microcontroller as a black box, and you test at the pins of the microcontroller. So all the signals at the microcontroller. That's the first level where you actually can test the complete software, including all the drivers. So the complete software as it is, as it's delivered to your customer. The next level would be the hardware in the loop test, the big hardware in the loop test with the power electronics, with the sensors, with the actuators. So you test the complete ECU. And the last level is the real system test, including all the hardware and so on. So that's something you need to do at the end of your product development, but you do not need to do this after every software change. The problem is a unit test is really simple and fast, so that's inexpensive, that's good. But the system test is really slow. You cannot do this very often, and it's really expensive. So with the Mini Hill, we're in the middle somewhere. So you have a complete automation. It's relatively inexpensive, but you already can test a lot of system properties with the Mini Hill. So now let's have a look at the response times for the test levels. A component test, for example, a unit or software integration test, is typically around a couple of minutes, maybe an hour if you have a lot of tests, but usually in an embedded system, that's more like in a couple of minutes. Integration test, hardware software integration test is usually not done. System test is already done every couple of weeks maybe. So there are actually very expensive tests that are done once at the end of the development, or maybe twice during development, because they are so expensive to do. And the acceptance test is also on a system test level, so that's also usually done not very often, so like the system test. So with the Mini Hill, you can run the hardware software integration test every couple of minutes. So basically every code change you can test with the Mini Hill. So on the right side, you see the Mini Hill for an Oryx processor, for example, the adapter board and the evaluation board here is provided by Hitex. And with such a setup, you can close the testing gap and get a very fast feedback in a couple of minutes for every code change. So now what can you do with this hardware software integration test? The main goal is not to test single software components, for example, the motor control or something like that, but the integration of the components into the software system, including the drivers and the electric system and electric signals such as PWMs, CAN bus, and so on. And by simulating the environment, you can put your system in almost any state to test it, just by changing the simulation for failure injection, for example. So temperature sensor, for example, can be simulated just by applying an analog output. This enables a very good automation, speed, and depth in your test process. An example that's basically the same example I gave you before about this temperature shutdown. Now you have a look at the microcontroller as a black box again, and we only want to stimulate at the pins of the microcontroller on signal level. So, for example, temperature shutdown is stimulated by providing an analog value, electrical value, and then your software, your black box behavior cascades through your system. Something happens. And in the end, what I really want to know for safety critical reasons, I want to know whether the system shuts down the motor control. So I want to measure whether the PWM goes off after 100 microseconds. That's the requirement here. And the other requirement is whether I get the right CAN error message, because, for example, if the pump or this lubrication system is attached to a crane, or to a windmill or something like that, to a wind generator, that's safety critical. So you need to know, you need this error message to react correctly. So that's what you can do as an example with such a black box test system here. Now let's have a look at the hardware. How do we do this? That's the Mini Hill board, the blue area. On the right side, you see an evaluation board, in this case, a STM32 evaluation board. I've shown you before the Oryx evaluation board for Oryx. So basically, you can add any kind of microcontroller, 3.3 or 5 volt, to the mini hill board. And the system on the test is usually the microcontroller here. So, and we connect all the pins of this microcontroller where your software lives. We connect it over this patch panel with the test system. And in this case, you see that's one of our customer applications here. Usually your microcontroller controls your system, but in order to test this, we simulate the environment with all the interfaces, the motors, the batteries, and so on, and make basically a virtual twin of your hardware and of your environment, and simulate the complete environment. And on top of that, we do the test cases, because, for example, if you have a motor, you need to control. If the motor is not attached, your system doesn't even get to the state where you actually can test something, because it fails before. So you need environment simulation, for example, the motor simulation, so that your system actually works. And then you can start to produce test cases. Here you can connect this with the typical low-level IOs like digital, analog, all the low-level bus systems, CAN, LIN, of course, PWM, and so on, UART, etc., etc. So now the main effort is not to connect the hardware. That's why we have the mini hill board that works out of the box mostly. So the main effort is to create an environment simulation your software can live in, and the test cases. So, and that's why we have a model-based development environment. It's called the mini hill software. So with the mini hill software, you develop the environment simulation and the test models. From there, we generate C code, we compile it, we flash it to this microcontroller here. That's our test system. And then the simulation and the test cases run against your system under test. And then we log everything, so all the results, the good case, the bad cases, and so on. And we generate a lot of diagrams, because the graphical diagrams are, for a human being, easier to understand than a text log. So that's why we produce a lot of diagrams in the end, so you can find your problems very fast. And in the end, you learn and you iterate. So that's how the software development for the hardware in the loop system works. Something special, since we have already a model of the environment simulation and the test cases, we can also generate combinatorial state transition tests. That's a very compact and a very structured way to create an expected or describe an expected black box behavior for your system under test. So you describe what you expect as a very compact diagram, state transition diagram, and then the system generates you all the test cases needed to cover all the paths through your system. So that's a very effective way and very efficient way also to find, for example, race conditions, sporadic errors, to really test for robustness of your system. So you would never do 500 test cases just to find out whether your system is stable or not. It's just too much work. Our code generator can generate 1 million if you want. That's really, really simple to do. So that's the second step, not the first, but that's something we can do because we already have the models to do that. So what does this look like on your desktop? If you're developing for one project, for example, you can hook up the mini hill directly to your laptop or to your desktop, and develop the test cases, develop your software. And when you change a test case, or when you change your system under test, you just rerun the software tests, the hardware in the loop tests. So that's a typical setup for one project, or for the test developer that actually develops the test cases and the environment simulations. If you have a bigger team, more products, for example, before I've shown you Kercher, they have a huge product line, many products they want to test. So they have more developers, and they have, of course, more products. So they're using continuous integration. So every code change of every developer is automatically built, tested, and delivered. So that's a typical setup, in this case for 8 different projects in a 19-inch rack. So for every project or for every product line, depending on what you do, you have a mini hill board attached to the continuous integration server, and wherever the developer sits, every commit is tested. So also for distributed development teams, that's a very good approach to get a reply for a test reply for every code change of every developer. So where is the mini hill used? So basically it's used in any kind of domain. We have customers all over the place, in automotive and avionics, in industrial applications, for example, handheld tools, or also in medical devices, micro invasive surgery, for example. I've mentioned Kercher before, cleaning equipment, high pressure steam cleaning equipment, and so on and so on. A lot of safety critical systems, but also just systems that want to save time and money by and driving the quality into the right direction. So basically everywhere where you have 16 or 30-bit microcontrollers, maybe an 8-bit, maybe 64, but with I/O you need to test with I/O functionality. So let's have a look at a little demo I'm giving you now. The demo test system on the test as a system under test. I have a microcontroller STM32. I'm going to show you this on my desktop here. So that's the system under test, STM32. That's the test system. Here I've wired all those signals. So the signals are 3 PWMs to control the BLDC motor. Then the test system measures the PWMs, starts the simulation once, calculates the new speed, and generates whole signals according to the new speed. So it's a real closed loop simulation, so that your motor controller actually does not know that it does not control a real motor. That's important because then you can bring it into any state you want. And the temperature sensor is just an analog value, an analog output, an analog input on the other side. And we have a UART to control the speed, to get error messages and so on. So typical small motor control project. That's already pretty close to a real world project, maybe with a couple of more IOs then. An example for on a signal level, what you can do with this mini hill now is, so here you see the PWMs generated by a system under test, then the Hall signals as digital outputs generated by the test system, by the motor simulation. And here you have the UART, RX-TX. Here that's the same diagram with a couple of more details here down. For example, here you have the PWMs, here you have the Hall signals, here you have the UART, and here you have the simulated temperature as an analog output. Here you see the boundary values of all the temperatures. And here you see the model speed as an analog output. That's to get a correlation, just to get a correlation between your test case, your stimulation, and what your test system actually thinks, or what your simulation assumes. Yeah? And now a couple of test cases. For example, over UART, you change the speed. What happens is that the system under test now slows down here. That's you can see this very good in at the PWM values here. The closed loop simulation reacts by slowing down the speed. That's what you can see. That's the speed that's actually measured by or calculated by the system by the test system. And the whole generator generates slower and slower signals. So it's a real closed loop simulation. The next test case would be a full stop after a motor temperature error. So the temperature's below the minimum. So I expect the PWM to shut down immediately. That's the example I mentioned before. So I want to know for a couple of maybe milliseconds or seconds whether the PWM stays off. And you see the motor simulation is a real simulation, so it slows down, so the inertia continues to drive the motor, basically. So the next test case would be a warning, temperature warning. So in this case, the motor does not shut down completely, but it gets slower. A typical limp home functionality, graceful degradation. So you do not want to shut down, for example, a safety critical system just because the temperature gets too high, but maybe you lower the speed in order to lower the temperature again. It's better to put on a little bit less grease for a lubrication pump than to stop the system entirely, because then your system fails completely. And the last example would be a recovery for the if the temperature goes in a normal range again, suddenly the motor recovers again, and that's also what you want to measure. And you can run this 100 times if you want. If you fear that the second or third time it's different, let it run 100 times, and then you are pretty sure that it works, maybe with different parameters. So now I'm going to my little demo. I'm going to run a little demo. So I have the Mini-Hill development environment here, and I have my real Mini-Hill connected to my development environment. So let's have a look at what we're doing here. I'm double-clicking to get inside the example here. Below here you see all the IOs. So I need an analog value for the temperature simulation. I need digital output adapter, a UART protocol in both directions. I need the PWM measurement for the motor simulation. The PWM measurement goes into the motor simulator over this port here. The motor simulator calculates the new speed after every measurement cycle. So basically with 20 kilohertz or something like that. And then it propagates the new speed to the Hall generator, which generates those 3 digital outputs. So that's the IO layer. The next layer would be the simulation layer. So the motor temperature just transforms degrees centigrade into an analog output between 0 and 3.3 volt or 0 and 5 volt. That's pretty simple. It's a bit more complicated to create a motor simulation, depending on your application, of course, on your motor simulation. You can integrate, for example, a Simulink model or other model. We generate C code from that, and we can integrate this. Or you can use also the modeling here for the behavior inside this tooling, for example, a state machine, to create a motor simulation. In this case, whenever PWM is changed, I calculate the new speed and I propagate the new speed to the Hall generator. So everything available in the model is you can use graphically here to program your environment simulation, your monitors, your test cases, and so on. In this case, for example, I could change the direction of the motor just by simulating the Hall generator into the other direction. So I'm simulating an error here, and by that I could provide a failure injection. That's a typical thing to do. So now with those 2 layers, basically your application already works as it's supposed to work, and now we have the test cases here on top of that. The test cases, that's also behavior, basically, but we don't create test cases as state machines. We could do this. We did this at the beginning, but if we know it's a test case, there are much more efficient ways to describe this. So we created a little test language here that also integrates, like the state machines, deeply with the modeling. So for example, if I want to activate something here, I can create a test step. The test step has actions and reactions. The reactions can be asynchronous. Also, the action can be asynchronous because it's an asynchronous system. So you do not get away with a synchronous unit test, for example. And you can use all the environment simulation elements, for example, the UART or the motor simulation, and change, for example, the direction. and wait for a reaction of your system under test. For example, I want to know the motor from the motor simulation, what's the actual speed, and now I can for example give it a speed between 200 and 300 RPM or whatever it is. So that's what I expect. And so with those steps, you create reusable test steps. And one level up, you can create then sequences. They can also be reused, of course. So the sequence here you see are always generated also as a documentation. You get a documentation as a sequence diagram. So whatever I change, you get a new documentation here. So you see the update here. And you integrate the sequences to test suites. And here, of course, in a test suite, you have more test cases and more steps here, also hierarchical steps and so on. That's good for the documentation. So that's what you expect in your test case. Now you can generate the test cases and the environment simulation and run it. So basically in this development environment, you can generate this, compile it, flash it to the target, and then run the test cases. I'm now connected with a little graphical user interface with the system under test. So, and now if I run the test cases, I'm going to pull a plug here. So that's a UART. I'm pulling a UART plug here. So let's pull this here and see what happens. Now I'm producing a lot of errors, yeah, because I did something wrong here. So basically it's not a software error, it's a hardware error I'm introducing here. And here you can see what actually happened and where the problem occurred. It occurred when I tried to send something over UART, because of course I disconnected the UART. So now if I click on this diagram, I get exactly the point in my model, where in my test model, where the problem actually occurred. So activate motor control, that's the test step. And I ran into a timeout because obviously my UART did not react. So I did not get an answer from the system under test. And that's exactly what I expected here, of course. So you can also run this not only directly on your desktop, like I'm showing you now. You can also hook this up to a continuous integration, like in this case, a Jenkins or a GitHub, GitLab, whatever it is you have, because everything I've shown you can also be done on command line. So it integrates really simple with a continuous integration server. But that's a story for another time. Next webinar will be about continuous integration with the Minihill. So if you're interested, please, please take part. Okay, so that's it so far. I hope you enjoyed the webinar. And if you have any questions, don't hesitate to contact either Michael Weiss from Hitex or myself from PROTOS. Thanks for your attention.